Yes, we are going indeed to switch gears from rising oceans and rising temperatures to the individual and to a major revolution that we have already started to undergo, and that's the revolution of personalized medicine. So we are already living quite long. It depends, of course, in the eyes of the beholder. Women in the developed world are living 84, 85 years, men 82, and that's up by almost 30 years from 120 years ago. So 4,000 years ago, we were living on the average 30 years. Now, only 100 years ago, we were living 50 years. And now in one single century, due to science and technology, vaccination, antibiotics, imaging, medicine, we have extended the lifespan by almost 30, 35 years, which is indeed amazing. And the question is how far we are aiming and how far biology can sustain us and what is the price. So the issue is very complicated. People are trying to predict lifespan. Of course, we cannot do it, mutations rate and so on and so forth. And medicine is moving in several directions. One direction is, of course, artificial organs, from hearts to bones to joints to the vascular system. The brain, of course, is still out of artificial organs, but maybe corrections in the brain are possible. Another direction is, of course, imaging and, of course, the classical development of drugs that have always accompanied us. So where drugs are going? So drugs the development of drugs is very interesting because initially drug development was incidental, and if you are thinking of aspirin, I'm not going because of lack of time to survey how many people in this very conference are consuming aspirin daily, but I'm sure that there are quite many of them. Aspirin was discovered by the old Egyptian 4,000 years ago. They discovered that it has pain alleviating characteristics, and then it took another almost 4,000 years to develop it as a drug for fever and inflammation by Bayer in Germany. And only a few years ago, it was discovered, about 3 decades ago, it was discovered that aspirin can prevent blood coagulation, and it has become the first line of treatment to prevent second myocardial infarction, which is blood coagulation in the coronary arteries that lead blood to the heart itself. And then its anti-inflammatory drug has been serving as the best, probably, chemoprevention for cancer, because the linkage between chronic inflammation and cancer has been discovered just recently. And for many patients who are cancer-prone, including colorectal carcinoma patients with a family story, aspirin has become a very good chemopreventive drug, and it has become probably the drug that has been consumed and is still consumed in tons, in amount more than any drug in the history of the pharmacopoeia. So this was discovered by coincidence. Of course, we cannot rely on coincidence for drug discovery, and we move penicillin by itself also was discovered by coincidence by Sir Alexander Fleming, but I will not go to the story. It's an amazing story. But we move to a more systematic drug discovery, which is screening, high-throughput screening. Drug companies are screening millions of chemical compounds against disease models. Disease model can be typically culture cells and later on animal models, but it has a limitation. It has a limitation because the models are not mimicking faithfully the true disease in the human being. And statins, for example, a very good anti-cholesterol drug, was discovered by screening of cells that are making excessive cholesterol by Akira Endo, a Japanese scientist, and statin has become a multi-billion-dollar selling drug to these days, and I'm sure that many people, again in this audience, are consuming statins daily. And but again, not all the drugs are acting equally on all patients. Statin have many side effects. It affects on cholesterol reduction only on some of the patients, not on all of them. And basically, it's very difficult for the physician to predict how a drug is going to act. And if we are thinking of a group of patients that's starting any treatment, we are color-blinded to us. Some of them will benefit from the drug, and some of them will not benefit from the drug, and even worse, some of them will develop side effects, and there will be a need to take the patients off the drug. And in the worst case, the drug will be beneficial, but the side effects are going to be so severe that it's intolerable for them to take it. So this led to the third revolution that we are now entering, and we are entering rigorously, and that's the personalized medicine. And the personalized medicine is based on a major achievement of scientists starting in the early 90s, where people decided to sequence the entire human genome, the 3 billion bases that makes us what we are, the individual repertoire. The first project was ended in April of 2000, was published in Nature, but since then we have made a huge progress, and the idea was to see how individual diseases are developed. So we know that cancer is a disease where tumors are developing, but there are several hundred types of cancer, and even if we are going into one individual cancer, like breast cancer, we realize that not all breast cancer are originating from the same mutations, and people are different from one another, and therefore no wonder that the same apparent disease is behaving differently in different patients. And if we look at breast cancer again, without going into details, you can see two different biopsies on the left side and on the right side of patients with breast cancer. The left patient is not stained with an antibody for a mutated estrogen receptor. The right sample biopsy is stained, so the woman on the right panel is suffering from a mutation in the estrogen receptor, and therefore should be treated with a drug against the mutation in the estrogen receptor, which is called tamoxifen. It will be useless to treat the woman on the left panel with the same drug. It will be waste of money, but mostly waste of hope. She has another mutation, can be in the EGF receptor, can be in the progesterone receptor, or she can be triple negative. None of the three, and nevertheless, she is sick and she has some other mutation. And by sequencing the genome of thousands of women with breast cancer, we now get a roadmap, and we realize already that there are 20 different types, or almost 20 different types of breast cancer. Each is derived from a different mutation, and therefore each should be treated differently. For some of them we have drugs, and for some of them drugs are still under development. So the story is, of course, the story of the individual. So the first thing, of course, it will be to stratify the patient according to the mutation she or he has, and then to decide about the appropriate treatment. But it's not all in the DNA, of course. It becomes much more complicated. Above the DNA, there are other levels of RNA, and above the RNA, there are the proteins that are actually the real cause of the disease, and proteins are undergoing different changes even after they are being coded by the DNA. It's called post-translational modifications, and all those developed in a very big way a new science which is called the science of omics, where we are getting information not only on the genome, on the genomics, but also on the RNA, on the transcriptome, the transcriptomic, on the proteins, on proteomics, on our general metabolism, metabolomics, and a whole new era is rising in front of our eyes, where we are profiling the patients systematically in order to get to a molecular diagnosis of the disease. So far, maybe so good. There are many question marks about the technology and so on, but I wanted to highlight at the very end of my very short talk some of the problems. Some of the problems are technological, and we are going to overcome them. I believe not all the diseases are due to one single mutation. Take, for example, one of the major group of diseases, psychological diseases like autism. They are derived from several mutations, and it's still very difficult for us to understand who is the driver of the car and who is the hitchhiker, and we need a much more significant statistics and population of patients in order to get to the real diagnosis of the mutation. But that's the technology. But I think that the main issue, or one of the main issues that we as an academy should pay attention is the ethical issue, and the ethical issue is extremely complicated. It's not only genetic privacy, because from now on, or from almost now on, each and every one of us and of the entire world population that will have access to modern health facilities once entering the operation theater or even the private clinic of the physician, will undergo sequencing of the DNA and probably a deeper analysis. And then many things are going to be discovered that are unknown to us. We came for diagnosis A, and we may exit the clinic with diagnosis B. For example, you come for a chest pain to rule out myocardial infarction, heart attack in the lay people language, and you may get out with a mutation that will lead in 5 or 10 years to the development of Alzheimer, and we know on such mutation, like A4B, or a mutation in P53 that may lead to cancer, and so on and so forth. So what we are doing about it, we are still healthy. The mutation is there, it's still working, or Parkinson's disease, or any disease. What we are doing with this information, if we cannot prevent the disease? The first question, of course, is whether the information should be available to the patient, to whom it belongs. And then once the patient knows about it, then what does he do or she does with it? Shall he go to his spouse? Well, spouse is still a reasonable possibility, but what about the employer? What about the insurance agent? What about the children? They may have inherited the mutation. So you see that the bioethical issues are really increasing as we think about it, and it's just behind the corner. Science and technology exceed in a very fast pace our ability to deal with the bioethical issues. And I want to end up just by giving you one example. So people know that be prepared for the big genome leak. There will be no way to hide it. Hackers will get into it, but we may be even obliged or forced to disclose this information, even to our future spouses. You know, we are getting married, we are falling in love. People want to be a little bit more formal about it. What do you have? What are the future prospects of the kids? And so on and so forth. And I'm not riding on the wings of my imagination. It's just behind the corner. And the last one, of course, is Angelina Jolie, that a few years ago came with the announcement that she's going initially to remove her breast and then her ovaries, because she discovered, due to a family history, that her mother had breast cancer. She was dying, now she is dead, and her aunt, the sister of her mother, died beforehand of ovarian cancer, 2 malignancies that are due to one single mutation, and therefore not all breast cancer, of course, it's rare, but nevertheless, the fact that 2 women, related women in the family, succumbed to diseases that are related to one another. She suspected that she's carrying a mutation in BRCA1, in a gene called breast cancer number 1. She was found positive to the mutation, and what she did, she took a preemptive step in order to remove a ticking bomb from her body. And again, she was lucky and unlucky in the sense that, lucky in the sense that the organs were removable. Not every organ in the body is easily removable. But on the other hand, again, there is a problem. For sure, Angelina Jolie doesn't have a problem with health insurance, but she does have a problem with the children. So what to disclose to the children and what not. I'm going to conclude by saying that we are not desperate at all in science. Technologies are behind the corner, fully loaded still with bioethical issues. Gene editing is behind the corner, CRISPR-Cas, Ziffinger, and so on and so forth. And we shall be able to correct mutations in the future, but again here, the slope is slippery, what mutations to correct, whether we are going also to edit human characteristics and so on. So you see, science is becoming more and more overburdened by ethical issues, and we should pay rather a very strong and serious attention to what accompanies us scientists in the laboratory. It's the role of the scientists to make the public aware of it, but scientists cannot carry the burden of solving this problem. It requires clergymen, churches, psychologists, sociologists, and the society at large, of course, legislating bodies and so on, to solve these major issues. Just one last comment. The Pontifical Academy of Sciences took seriously this issue, and in April we are going to conduct here a 2.5 days workshop on the bioethical issues of personalized medicine. Thank you very much.